In this last video, I've even started it out just for fun. What I want to talk about a little bit is Fermat's last theorem and how it's related to all of this stuff that we're doing in abstract algebra. So this is not the type of stuff that you're going to be tested on, but this is a really cool and awesome piece of mathematical history. And to keep you interested in paying attention for the rest of this, or from just closing this video right now, at the very end I'm going to have your summary with lists of things that you should have learned from all of the videos that we've covered. But first, let's talk about Fermat's last theorem. So something that you've probably noticed ever since a high school geometry class is that there's infinitely many integer solutions to the equation x squared plus y squared is z squared. So you first see this with 3, 4, 5 triangles. You see this with 5, 12, 13 triangles. Those are the ones people generally have memorized. And then there's a whole bunch more that you can find. Now, mathematicians like to take numbers and change them all to letters and then ask if everything's still the same or not. So after we figured out, people found it generally interesting that you could have this 3, 4, 5 type situation, 3, 4, 5 triangles. And so they said, if I change that 2 to an n, how many non-trivial integer solutions are there to the equation x to the n plus y to the n is equal to z to the n for n greater than or equal to 3? By non-trivial I mean, of course, if I pick like 0, 1, and 1, that's going to be a solution, but we're looking for interesting things like the 3, 4, 5. Now, the real answer to this is that if you make n be a number bigger than or equal to 3, there aren't any non-trivial integer solutions to the equation x to the n plus y to the n equals z to the n. In particular, there are no integer solutions to the equation x cubed plus y cubed is z cubed. And it doesn't matter if you change the cube to a 4th power or anything higher, you're still not going to find any interesting answers. And so that makes this 2 case really kind of nice and unique and special. The thing is that there's a mathematician in the 1600s named Fermat, and he it's actually kind of a misnomer for me to call him a mathematician because he did math more or less as a hobby. He wasn't doing this as a job, he wasn't a professor of mathematics, he wasn't writing papers for mathematical journals. He just did math because he thought it was fun. So with that respect, he was just kind of a puzzle person. He kind of liked mathy puzzles, so he wasn't ever in the business of writing up solutions nicely and cleanly for people. He was just in the business of kind of convincing himself that something was true, and then he would move on. So according to this fact, he was interested, he knew of the integer solutions to the equation x squared plus y squared is z squared. He was interested in the question x to the n plus y to the n equals z to the n, where n is arbitrary, greater than or equal to 3. And apparently he thought about the problem and jotted down in the margin of one of his books this marvelous quotation that has now gone down in history. I have discovered a truly marvelous demonstration of this proposition, which this margin is too narrow to contain. So he realized that there were not any non-trivial integer solutions to the equation x to the n plus y to the n equals z to the n. He seemed to think that he had convinced himself that this was true, that his proof was truly marvelous, but it was just a little too long for the margin of the book. And not being a professional mathematician, why would he bother to write it up? He convinced himself it was true, he had the proof, it was in his head, and that's all he really needed. Now, upon Fermat's death, people sort of started going through his things and realizing that he was actually quite a good mathematician, and there were a lot of awesome facts that he seemed to have convinced himself of, and said, oh, did you know that this was true? Did you know that this was true? And sometimes people did, and sometimes people didn't know that it was true. But it seemed as though even if he said something was true and he didn't mark a proof of it down, people seemed to be able to come up with a proof later. And so when Fermat wrote something down and said, oh, this is true, there's a nice little proof of this, it was almost always the case that somebody would come along and say, yes, indeed, that is true, and they would find a nice little proof of this. Now, one by one, after Fermat's death, people started filling in these proofs and finding out these little puzzles that Fermat had known, and they were proving them one by one. And the very last of these conjectures to be proven was there are no non-trivial solutions to the equation x to the n plus y to the n equals z to the n. After Fermat's death, this conjecture was worked on. When this was dwindled down to be the last conjecture that he had left, this was worked on by almost every mathematician of of influence over the course of history from the time of Fermat's death to modern day. That includes Euler, Gauss, Legendre, Abel, Dirichlet, Kummer, Germain, and Hilbert. All of these huge names that you'll know if you study any higher level mathematics. They all worked on this, and they could not come up with Fermat's proof. Again, we should find this really surprising, because as clever as Fermat was, and as much of a fun little puzzle maker he wasn't a mathematician. He was not a classically trained mathematician. Gauss is one of the top 3 mathematicians of all time, and Gauss couldn't do it. Right? That makes me terrified. I wouldn't dare to work on it. And so for hundreds of years, this conjecture was open, and people seemed to think that there was this really clever little proof that Fermat had known, that we just weren't finding. We just weren't coming up with the cleverness of his proof. Now, there was another mathematician known as Lamain, and he was very good. And there were others, in fact, that claimed to have come up with a solution to Fermat's last theorem. So one thing that you can do is you can simplify. You don't need to consider x to the n plus y to the n equals z to the n for all n. It's enough, if you believe it, to consider primes. So people would look at the equation x to the p plus y to the p, and they would use complex numbers. They would factor this polynomial in 2 variables as x plus y times x plus alpha y times, and so on and so forth, all the way out to x plus alpha to the p minus 1 times y, where p is some sort of prime number, and alpha is what's called a primitive p-th root of unity. So that means that alpha is a somewhat nice solution to the equation x to the p plus 1 equals 0. It's a primitive p-th root of unity. And it's in fact correct that x to the p plus y to the p factors this way. And since z adjoined alpha, if you just take the integers and you throw on alpha, that's a domain, you find from setting any one of these terms equal to 0 that x is going to be negative alpha to the ith power times y, and that's going to imply pretty easily that you can't have x and y both being integers, because this number alpha is definitely not an integer. So Lamain and the many others who came up with this solution claimed that there were no integer solutions to this equation, and all you really needed to do was use complex numbers and factor in this way. And so many people, when they would stumble upon this proof, said, aha, I've got it. I've got the proof that Fermat had. It's a nice, clever little proof. It's pretty short. Doesn't involve anything too fancy. Right? And they'd say, I've got it. I've got the proof. Right? The problem with this is that when you take z and you adjoin alpha, which is a primitive p-th root of unity, this is not always a unique factorization domain. And so it is correct to say that these solutions would not give you integer solutions. If you factored in this way, these are non-integer factors. However, the problem is that there isn't unique factorization here. So the error in this would be, going back to our early example, taking a number like 4 and saying, aha, 4 factors as 1 plus the square root of negative 3, that quantity, times 1 minus the square root of negative 3, and neither of those terms are integers, so 4 does not have an integer factorization. However, that's incorrect when you're not working in a UFD, because you could also take 4 and factor it as 2 times 2, and each of those are integers. So you're running into this problem with saying, aha, I've factored it, this is the way to factor it, and I don't have integer solutions here. The problem you're running into is there isn't a the way to factor it in the space that you're working in. And so all these mathematicians who claim to have found the short proof, the clever proof, the proof that they thought Fermat had, they had this error, and the error was that they weren't working in a unique factorization domain. So studying and understanding what it means to be a unique factorization domain was a really big and awesome and interesting problem in abstract algebra for a very long time. As people wanted to know, if I'm not working in something that's a unique factorization domain, what am I working in? Because this is really different from the world of numbers that I know. And so this was historically the study of unique factorization domains and how they play into one of these greatest mathematical puzzles of all time. What I should say is that it's really, really interesting to read about the history of Fermat's last theorem, or I do. Being a math person, I think that this is unbelievably interesting. There's an awesome book that can be read by people who don't have the largest mathematical knowledge called Fermat's Enigma, which is a really nice book, which is a very gentle math introduction to just what is the problem, who worked on it, who made important contributions, what were the important contributions, and so on, all the way up through Wiles's proof of this awesome, awesome fact. Then there's a Nova special that called The Proof, which goes over the history of the problem as well, which is a really awesome documentary. I couldn't find it on Netflix, but I could find a transcript of this available through PBS. And I don't know, maybe if you can actually rent movies from Netflix instead of just doing streaming, you could find it and watch it, and that would be pretty cool. Unfortunately, so I've taken your knowledge of Fermat's last theorem, other than just there are no solutions, and the proof of it is really hard, and it wasn't solved till the 1990s, and hopefully I've elevated it to understand one of the big complications with this problem was that people didn't understand for a long time that there could even exist things that weren't UFDs. And in fact, it's generally thought of that the proof that Fermat had, proof quote-unquote, was incorrect. Most mathematicians believe that Fermat did not have a correct proof, that he had the incorrect proof, assuming unique factorization of the domain Z adjoin gamma, or Z adjoin alpha, I should say. That was the notation I used here. If you want to go the step further, and you really want to understand the whole proof of Fermat's last theorem, such a thing exists. There's a course offered on the proof of Fermat's last theorem by one of the world's leading experts on this proof, Dr. Nigel Boston, who's phenomenal. He offers a whole semester-long course that goes through the proof of Fermat's last theorem. It takes all semester to prove the course, and you need a couple years of graduate school to do it, but it's really awesome if you can. And I put his website up on here because he has class notes. He had somebody from the course take notes every day, so in theory there's a slightly more accessible version of the proof than the paper that Wiles wrote. It's in the Annals, and you can read this at his website, and he also has tons and tons of information on Fermat's last theorem. He knows Andrew Wiles in person, they're kind of buddies, so he's a cool dude as well. Alright. Jumping ahead to the summary. After studying these slides and your textbook, you should understand all of the main definitions here. So you should know and understand the definition of a Euclidean domain, a PID, a UFD, and an Euclidean ring. You should also understand the hierarchy that relates these notions. So you should be able to give examples when they've been provided for you of rings that have these specific properties. What you'll be asked to do on your homework is I'll give you a handful of domains, and you need to kind of take a look at them to see what you can understand in order to classify something as fully as possible. You should also be comfortable using the properties of the norm map that we discussed early on in the video in order to determine if particular elements of Z adjoin gamma are irreducible, if they're prime, etc. That's really a good way to talk about when elements are irreducible or prime or not. And last but not least, you should be prepared to use the various properties at play in different types of domains in your own proofs. So you should be able to use something like, what does it mean for this to be an Euclidean ring? It means I need to find a chain of ideals somewhere and argue that it eventually terminates to help me out. And also, if you're given that you're working in a principal ideal domain and somebody gives you an ideal, you should be able to say, aha, that means this is the ideal generated by R for some R in the domain, and so on and so forth. So you should be prepared to not just understand the definitions of these various types of domains, but to use their key properties in order to write your own proofs.